Hello, everyone. My name is William K. Moses Jr., and I'll be talking about singularly near-optimal leader election in asynchronous networks. This is joint work with Shai Kutten, Gopal Pandurangan, and David Peleg. And of course, you can come see my talk live on October 7th at DISC. So in this talk, I'm going to first explain the problem to you. Then I'm going to tell you why you should even care. After that's established, I'll explain the algorithm, the nuts and bolts of it. And finally, I'll give a few open problems. So let's jump into this problem itself. What is leader election? What's a problem we're trying to solve? There are a bunch of nodes, and all of them want to participate in an algorithm to do the following. They want to elect a unique node that's recognized by all the other nodes. And subsequently, they all should terminate. Now, looking at the model a little more closely, we see that there are n anonymous nodes, which is to say these nodes don't have IDs. But the value of n is known to all nodes in advance. So that this number, like if there are 27, it's known to all the nodes. These nodes are connected in an arbitrary graph. And we consider the congest model, which is when messages are sent along an edge, the message size is restricted to O log n bits. We assume adversarial wake up. What that means is, initially, some nodes might be asleep and some might be awake. And the way the node wakes up is in one of two ways. Either the adversary wakes it up, or an awake node might generate a message and send it to this node, which results in this node waking up. Finally, we consider the asynchronous network. What that means is the delays on messages are arbitrary. So for example, if this node sends out 2 messages, it could be the case that while this node message is still in transit, the other one reaches this node, is subsequently sent to this node, and in fact reaches this node, all while this is in transit. Now, that was a model, but for the algorithm, how do we measure the goodness of our algorithm? What are the performance metrics we use? We have 2 metrics. First, the time from when the first node is awake. So what is the setting? Initially, all nodes are asleep, and then the adversary wakes up a non-zero subset of nodes. From the moment this non-zero subset is awoken, time starts. And what is time here? Well, if you consider an execution of the algorithm, look at the entire execution, and then consider the maximum message delay on any node. That maximum delay is now considered 1 unit of time, and all the other times are normalized to this. So metric 2 is how many messages is generated and sent in the course of this algorithm. And in our paper, we have these words, singularly near optimal. What does that mean? Well, an algorithm is singularly optimal if it's both optimal in time and messages. And it's near optimal if it's only off by polylog n factors in either of these 2 metrics, or possibly both of them. Now, with the setting out of the way, I'll tell you why I should care. First of all, why care about this problem? Well, this is a fundamental problem with numerous applications. For example, leader election is used as a primitive in minimum spanning tree construction, or in breadth-first search tree construction. So it's used as a primitive. And by itself, leader election is also of vast importance. If you want to coordinate entire network, having one node elect itself as a leader is very important. I also want to mention, this problem has been studied for many years, as far back as the 1970s. It's been studied quite a bit. So this is why you should care about leader election. Why care about this paper in particular? Well, this paper I mentioned, we have near singularly optimal results, but it's important to look at these in the context of history. Typically, papers, when they solve leader election in asynchronous networks, arbitrary networks, they've either optimized for messages, where omega of m is a lower bound on the message complexity, while giving up on time, because omega of d is a lower bound on time, and n could be much larger than d. So either they optimize on messages or they optimize on time. So for example, Peleg's result from 1990, O of D message complexity, but O of MD time, O of D time complexity, but O of MD message complexity. The closest that any paper came to optimizing both parameters simultaneously was Auerbach's paper from Stock 89, where he has an m power 1 plus epsilon message complexity and d power 1 plus epsilon time complexity, where epsilon is any value greater than 0. So we improved this to m log squared n and d plus log squared n. And it should be noted that some of these past results have been deterministic and some have been randomized. Our own algorithm is randomized. Now, why should you care about this talk? What are you going to gain from this talk? Well, first of all, the algorithm that I'm going to present is quite simple. So it's easy to understand the entire algorithm if you just listen to the talk. Subsequently, another reason why you should care about this talk is that I will give some intuition for the design choices we made. And finally, in this talk, I'm going to talk about the correctness, and I'll give analysis for time and message complexities of the algorithm. With all that out of the way, let's jump into this algorithm itself. Recall that we're solving leader election in an arbitrary graph in an asynchronous network with adversarial wake-up. In this setting, for this problem, we design a randomized algorithm that solves leader election with high probability. And the message complexity is m log squared n with high probability. So log squared n factor away from optimal. And with time complexity, O of d plus log squared n with high probability. So an additive log squared n factor away from time complexity. So what are some basic ideas involved in the algorithm? Well, in this network, we will have a subset of the nodes become candidates, and these candidates will compete to be the leaders. In order to break ties between these candidates, we have another subset of nodes elect themselves as referees. And finally, whenever I want to communicate a message, even if this node wants specifically to get a message to this node, we use a simple broadcast, a simple flooding primitive to ensure that messages reach the desired target node. So if there's a message here, just spread it or flood it. These nodes propagate the flooding until the message reaches everyone. And importantly, in this leader election setting, some nodes, all the nodes initially may or may not participate, but all the nodes will be awake, and some of them will be candidates, and the others will be non-elected. The goal is to reach a situation where one of these candidates becomes the leader and every other node in this network is non-elected. All right. Now, in order to get to this design algorithm, we have to do a little pre-processing first. First of all, these nodes are anonymous, so we need to distinguish between them. We can do that by having each node choose a rank or an ID between 1 and n power 4 uniformly at random. This guarantees that the IDs in the network will be unique. Each node will have a unique ID with high probability. Now, we need to elect candidates and referees. How can we do that? Have each node flip a coin with a probability 1000 log n by n. This will guarantee that on expectation, there will be 1,000 log n nodes that are candidates and 1,000 log n nodes that are referees on expectation. The only catch is there's adversarial wake up. So the adversary might initially just wake up too few nodes, which results in the following situation. When they flip coins, not enough nodes were awake, so no candidates come up. Because at the end of the day, only a candidate can become a leader. In order to deal with this, we ensure that all nodes are awake before we have them flip. How do we do that? When a node is awake, it sends a special wake-up message to all of its neighbors. This wake-up message is just propagated until all nodes are initially awake. And then they can flip the coins and move forward with their lives. Now, in this competition, what happens for candidates? Well, candidates, let's say, for example, 15 is a candidate, and 15 is the ID or the rank of that node. Now, it broadcasts its desire to be a leader, sends a message, 15 wants to be a leader. Now, it will wait for the first 900 login replies. Recall that on expectation, there'll be 1,000 login referees, but we only wait for 900 login of those replies. Subsequent replies we can discard. And what is a reply? It's basically the form referee R says accept or reject about you, the candidate. Now, if all of the replies, these first 900 replies are accepts, well then the referee becomes a leader. I'm sorry, the candidate becomes a leader, and it broadcasts a win message, which is, I am the leader, now terminate the algorithm. And it's all good. But if even one of them is a reject, then it becomes non-elected and it broadcasts its loss. That is, 15 says, oh, you know what, I lost, discard me. We should also note that it's not just if one of the first 900 messages is a reject. If before receiving 900 login replies, the node receives a dispute, then also it becomes unelected. And what is a dispute? I'll get into that. I'll get into more details in the subsequent slides. But for now, it's a special message that's been generated by some other referee that basically says candidate 15, the candidate's ID, versus some other candidate with the higher ID. What this implies is that there's another candidate with a higher ID that wants to become the leader. And so before these first 900 replies come, if this candidate hears about a dispute, it gives up its candidacy and it'll let that guy win. Now, what's happening with the referees? Well, consider referee R. It keeps track of which candidate it said, yes, you can become a leader to. So initially, it's not said yes to anybody. So the first time it hears about such a candidate, any candidate, it generates accept the message for that candidate, which is basically referee R says accept about that candidate ID, and it'll store his candidate's ID. Subsequently, let's say that referee R hears a message about some candidate C2. Now, either C2 will have a smaller rank or a larger rank than C1. Let's look at what happens if it has a smaller rank. In this situation, the referee rejects C2. What we're trying to do here is we're trying to, ideally, the candidate with the highest rank will become the leader. Now, that may not be the case, but this is what this procedure will lead to. So suppose now that you hear about another candidate C3, but it actually has a higher rank than C1, which is the candidate R has already said, yes, you can become leader to. Thing is, in order to ensure there's no inconsistency in the system, that is, to make sure that C3 doesn't think it's been given the go-ahead and C1 doesn't think it's been given the go-ahead, R offloads the work of deciding which of these two will be allowed to become the leader to C1. How does it do it? By generating a dispute message. which is what we talked about in the previous slides. What is that? It's basically of the form candidate C1 versus candidate C3. It's just asking, all right, candidate C1, have you already become a leader, or are you still in contention? Because if you're still in contention, then eventually when that dispute message reaches the C1, C1 will lose its candidacy, and it'll generate a C1 loses message. That message will eventually make its way back to the referee, and the referee will say, oh, you know what? C3, now you can become the leader. And it'll generate a accept message for C3. And importantly, this dispute message has generated. If C1 lost out, okay, then C will eventually lose out here, and C3 will be announced as a new leader, as a possible new leader, or at least R will generate an accept for C3. If C1 actually became a leader, then it would have already generated a leader announcement message, which renders any further computations by this referee meaningless. So that's why the referee will just wait until it eventually gets this leader announcement message, and then it'll just propagate that message and terminate. Okay. Now, that's pretty much it for the algorithm. Like I said, fairly simple. Now let's look at the analysis. There are 3 things to prove. First of all, correctness, then message complexity, then time. Let's look at correctness first. So if you want to talk about an algorithm, if you want to prove that an algorithm solves leader election with high probability, we should first show that at least one leader is elected with high probability, and then at most one leader is elected with high probability. So we'll show these 2 things in subsequent slides. Before that, it's important to note 2 things. First, all nodes will be awake in OFD rounds and OFM messages. Second, because all of these nodes are awake initially, they'll be able to participate in the referee and candidate election. And that leads us to the following lemma, which is the number of candidates and referees is within 900 login and 1100 login with high probability. So now let's focus on this correctness. At least one leader is elected with high probability. How do we show this? Well, we know that at least one candidate exists with high probability. And we know that for any candidate that exists, it's going to receive at least 900 login replies because it's lemma. Now, from all the candidates, let's consider the candidate C that has the highest rank. Now, in this case, if it reached all the referees first, then it'll be elected as a leader because all of them will say yes. And even if it reaches a referee secondly, it has a higher ID. So unless higher ID than any other competing candidate. So when those disputes are generated, assuming none of the other candidates became a leader already, then this guy will win the dispute and it'll get an accept message, which leads it to becoming the leader. The only time it won't become the leader is if it loses too much, which implies that some other candidate has become the leader. So now we've shown that at least one leader is chosen. What about at most one leader is chosen with high probability? Well, for any 2 candidates, C1 and C2, we're going to show that they share a common referee among the first 900 login replies. So let RC1 be that set of first 900 login replies for C1, and R2 be that set for C2. Now, it's easy through a little bit of math, thanks to this lemma, to show that the intersection of these 2 sets is non-zero. So with that shown, we show now that when 2 candidates share a common referee, at most one of them can become the leader. In the course of showing this, let's assume that without loss of generality, the rank of C1 is smaller than rank of C2. Now, there are 3 cases that cover all possible situations. In the first case, the referee already knows about some other candidate, C3, and C3's rank is greater than C1. In this case, Even if C1 if that candidacy message is heard, it'll be rejected, in which case C1 won't be the leader. Now, alternatively, instead of this being the situation, it could be that C3 has become a leader before any dispute message generated by R reaches it. Thing is, if C3 has already become some leader, well, neither of these other two will become leaders, because C3 became a leader, R knew about C3, and if C1 comes, it's outright rejected. If C2 comes, if it's larger than C3, then it would result in a dispute. And this dispute won't change things because C3 already became a leader. So in the other case, C1 or C2 won't be the leader. Next, we'll consider a situation when R already knows about C1 or already knows about C2. If R already knows about C2, and basically it's already said that C2, you can become the leader, all before C1's candidacy message reaches R, then C1 will not become the leader because C1's rank is smaller than C2. On the other hand, C1's candidacy message, suppose it's already, C1's message reached R first, and R said, yeah, sure, you be the leader. And subsequently, C2's candidacy message reaches R. Well, then a dispute is generated. And once a dispute between C1 and C2 is generated, that'll ensure that one of these two will not become the leader. So in all of these three cases, at most one of them might become the leader. And since it's between any two candidates, C1 and C2, and all candidates share at least one referee with all other candidates, we know that whoever the leader is, he shared a referee with everybody else, which guarantees that if he's the leader, none of the others are. And so that's correctness. Now, when it comes to messages, first of all, we have the observation that all nodes are awake in O of D rounds and O of M messages. So O of M comes from there. We also have this lemma on number of candidates and referees. Now, the thing is, we can show that each candidate and a referee generates only O of log n unique messages. Candidates really only generate three types of messages. One is a candidacy message saying, I want to be the leader. Another is a loss message. If it loses a dispute, it'll broadcast that, okay, I have lost. And the third type of message is a leader announcement message, which only one node really does. The referees, on the other hand, can generate O of log n type messages where, first of all, replies to candidates. There are O of log n candidates and one type of reply, either an accept or reject. And also dispute messages. But since they're, again, log n candidates, they're only going to be O of log n disputes that can ever arise from this given referee. So aside from these candidates and referees, non-candidate referee guys will not generate any unique messages. And overall, entire network, there'll be one unique wake-up message. So in sum total, there will be O of log squared and totally unique messages that are ever generated in the network. And each of these messages, in order to be communicated to others, a broadcast is used, a flooding is used. For flooding, O of M messages are required. So in total, O of M log squared n messages are needed. Now, as for time, the totally, as I mentioned, log squared n unique messages. Consider some arbitrary execution. Let C1 end up being the leader. Now, there are O of 1 logical phases of the algorithm. What does this mean? It's basically a sequence of things that need to happen until the leader is elected. First, nodes wake up, then C1 broadcast candidacy. Referees might need to generate disputes. Those candidates that lose the disputes have to reply. Referees then subsequently broadcast accept to C1. And finally, C1 broadcasts its leadership. So this sequence of steps, there are O of 1 such steps. And for each step, let's look at the time it'll take. So we have a lemma from Topkis that says, if you have a diameter d graph in an async setting and you want to broadcast k messages, it takes d plus k minus 1 time. So in each phase, log squared n messages and diameter d, so O of d plus log squared n time. So totally, since they're O of 1 logical phases, the total time is O of d plus log squared n. And I want to note that these phases, this is not some implementation in algorithm. This is just something for the sake of analysis. So with that done, analysis is over. And I just want to wrap this up. First of all, in this talk, I gave you the algorithm. In the paper, there's a little extra. Basically, in the algorithm, we assumed exact knowledge of n, but you can loosen it up to a constant factor knowledge of n. The open problems. Our algorithm was randomized. But can you do it deterministically? Next, we have a loosening up to constant factor approximation on n, but can you still solve this problem if you only know a polynomial approximation on n, or in fact, if you even don't know n? Finally, can we get near singularly optimal algorithms for other problems? So with this, I just want to wrap up. These are some of the references. And of course, I'm very grateful for Creative Commons, and so I could use some nice images. And with that, I just want to say thank you.